we're going to look at what's called margin of error for population proportions. In our opening exercise here, they're giving us these sample distributions that kind of how we did with the coins, except now it's a number of red chips in a bag. Okay, so 9 different bags of colored chips were distributed to small teams of students in a class. Each bag had a different proportion of red chips. So on the front page, you just have, it's already done. There's nothing really to do there. This is just what we're going to be using to do the problems on the next page. So the sample size was 50, okay? And each dot represents how many red chips that they pulled out. So as you could see here, okay, here you see a lot of them pulled out 5, centered around 5, right? Around 5 red chips. Well, that's because this bag had 10% red chips. 90% were some other color, okay? Well, what's 5 out of 50? 5 out of 50 is about 10%. That's why a lot of them were around 5. Not every single one was 5, just like with the coins. It wasn't always 50%. Sometimes it was 0.4, sometimes it was 0.6, but it was around 5. Okay, then this bag, it's a different bag. 20% red chips. Well, look at how 10 is kind of the middle, okay? And then 30 red chips. Looks like 15 is the middle. 15 out of 50. 30% red chips. 40% red chips. Well, when they're pulling from a bag with 40%, they're getting more red chips in those samples. More and more red chips. 50% more red chips. 60% I'm getting more and more red chips. When I go to 90%, that means the bag contains 90% red chips. If there's 1,000 chips in the bag, 900 of them are red. Almost all of them are red. So it's expected that if I pull out 50, I'm going to get a lot of red. Well, it looks like they got about 45, 46, 47, 44, 43. They got a lot of red chips in every sample. They kept pulling out 50, right? They got 45, then they got 43. That was done a lot of times. So we didn't want to simulate this in class because it would take 2 classes just to get this data. All right. So now we're gonna take a look at some questions here based on these. We're gonna go all based on these mystery bags here. Okay. So suppose you drew 30. You're gonna draw 30 red chips in a random sample of 50 from the mystery bag. What are the plausible values for the proportion of red chips in the mystery bag? Okay, so if you drew 30, what do you think the proportion would be? So you're gonna do 1. You're pretending that you're doing this group. You drew 50 chips out, right? And you got 30 red. Do you think the bag was 10% red? If you got 30 red, do you think it was 10% red? Well, if you look at what happened in the past here, it's probably not, because the smallest was like 2 and the biggest was 10. So I doubt I got 30 red chips, so it wouldn't be that one. This one, it's doubtful I got 30. This one, it's doubtful that it came from 30. This one, it's doubtful. Okay? 30, yeah, maybe here. Maybe 50% red chips, because I got a 30 there. 30 is likely here for 60% red chips. And even 30 here, 70% red chips. You think it was 30 here? Probably not. You think it was 30 here? Almost definitely not. So 50, 60, or 70% would be likely. So I would say for the proportion, it would be 0.5, 0.6, or 0.7. Okay? So let P represent the population proportion of red chips in the mystery bag. Based on your answer to part A, write an inequality that describes the plausible values for P. So what do you think P could be? Well, we just said we think 50% is the lowest and we think 70% is the highest. We very, very, very doubtful it's less than 50%. Could it be? Sure. Very, very doubtful it's more than 70%. Could it be? Sure. But probably not. Probably between 50 to 70%. So we're going to write that as an inequality. P is the proportion. Since 0.6 is the middle, Well, we don't care about the middle in this one, actually. We're just going to say P is greater than 0.5, less than 0.7. So we think the proportion of the population, now we don't know the population, we're using sampling to guess, we think it's between 50% and 70% based on the fact that we drew 30 red chips and looking at the data on the front page. So that's an inequality. So margin of error for a sample proportion is based on this inequality here. We take the middle of the inequality. So what's the middle? We're doing this number 3 now, okay? To do number 3, using this notation they're talking about here, we need to find the middle of that. The middle of the 0.5 to 0.7, we're going to call that our p-value, our expected p-value. 0.6 is right in the middle. All right, we're going to write that as in this notation right here. So if 0.6 is the middle, I said we can go down to 0.5 and we said we can go up to 0.7. So we can go 0.6 plus 0.1, that would be 0.7, or we can go 0.6 minus 0.1, and that would be 0.5. That would give us our two extremes, right? So we're going to write it in this notation, 0.6 plus minus 0.1. That is the interval notation that we're going to be using here when we're talking about margin of error. All right. So number 4, what is the margin of error? Well, the margin of error is the distance that you're going each way from our expected middle. So the middle, the p-value is 0.6, and the middle of that expected what we think, and then the margin of error can go each way. So we're going 0.1 in each direction. Therefore, the margin of error, we're going to call it M. M equals 0.1. So the margin of error would be 0.1 for this sample because we went the middle and then we went 0.1 each way. Now, standard deviation, turns out we can calculate the standard deviation based on how, if we know the proportion and how big the sample is, okay? So below are 2 simulated sampling distributions for the sample proportion of female students and random samples from all students at Union High School. So here's one and here's another one. All right. Based on the 2 sampling distributions above, what do you think is the population proportion of female students? So let's take a look here. What do we think is a proportion? Well, what's the middle of all this? What's the middle of all this stuff here? Looks like it's right about here, right? Okay, right at about 0.4, and right here looks like the middle is right about 0.4. So it didn't matter the sample size, which just like the coins, the sample size didn't matter. We were right around 0.5, right? Well, we're right around 0.4, right around 0.4. So that's our proportion. We're going to call it 0.4. One of the sampling distributions above is based on random samples of 30, and the other one's based on random size samples of size 60. So which one do you think was the bigger sample size? Remember, from our last lesson, this is just from our last lesson, the bigger the sample size, the smaller the deviation, the more the distribution is going to squish together. Okay? So which one is more spread out? This one is more spread out. These are closer together, right? So this right here is the smaller sample size, 30, and this one is the larger sample size, 60. Okay, so we'll say distribution 1 is 60, and distribution 2 is 30. And just explain it. You would have to explain it if they wanted you to explain it. Just exactly what we said. Larger sample size, smaller standard deviation. Find the standard deviation for each of these distributions. Now we have a form. We're going to use our formula to do that. So here's our formula right here. Square root of p times 1 minus p divided by n. All right, so for distribution 1, our standard deviation is going to be the square root of p, we said 0.4, times 1 minus p, 1 minus 0.4, divided by n. We said distribution 1 had a sample size of 60, so divide by 60. literally just put that in your calculator. 0.4 times 0.6, divide by 60, take the square root. I did it ahead of time just to save us time on this video, and it comes out to be 0.063. Now let's see how that compares to our deviation for distribution 2. Distribution 2, okay, square root of 0.4 times 0.6, same, 1 minus 0.4, and divide by 30 now. Dividing by a smaller number is going to give us what? Okay, it's going to give us 0.089. It's going to give us a larger standard deviation. So the smaller the sample, the larger the standard deviation. You could see that. Smaller sample, larger deviation, larger sample, smaller deviation. All right? And for each of these distributions, find the interval containing all sample proportions that fall within one deviation of the mean. So for distribution 1, we got 0.4 as our proportion, and we're going to add our standard deviation, 0.063, and then do 0.4 minus the standard deviation of 0.063. Okay? So that gives us a p-value, we say, between 0.337. Oops, sorry. This is 0.337, and no, it's not. This is 0.337, and this one is 0.463. Okay, so our p, I just got to go down here. Our p should be greater than equal to 0.337 and less than equal to 0.463. Okay, that's our inequality there. For distribution 2, all right, 0.4 is our proportion. We're going to add our standard deviation, and we're going to subtract our standard deviation. 0.489, and the other one is 0.311. So we'll say P is greater than equal to 0.311, less than equal to 0.489. So we would expect the real population proportion to fall between 0.311 and 0.489. That's within one standard deviation of the mean. If you go one standard deviation of the mean each way, it's 0.311 to 0.489 for the distribution 2 and 0.337 to 0.463 for distribution 1. All right, example 2 starts talking about margin of error, which is the whole point of this lesson. All right, in the work above, you investigated a simulated sampling distribution, the proportion of female students in a sample of size 30, drawn from a population with a known proportion of 0.4 female students. Here's the simulation. Use the formula for the standard deviation of the sample proportion to calculate the standard deviation of the sampling distribution. I know that's confusing. They're asking you to find the standard deviation, basically. So standard deviation we know is the square root of, we need P, okay? So P is 0.4. 0.4 times 0.6, because that's 1 minus P, and then divide by N, and we says the sample size was 30. So divide by 30. We actually already did this exact calculation. It's right here. So we already know it's 0.8. It's 0.089. Just a different distribution, but it was the same numbers. Okay. On the dot plot, mark off the sample proportions that are within one standard deviation of 0.4. All right. So we already know those two, right? We just did those. It's right here. It's 0.311 to 0.489. Okay. So let's do that. Let's first draw our normal curve here over the dot plot. All right, so where is 0.311? Right about here. 0.311 right about there, and 0.489 right about there. Okay, and then that right there is within one standard deviation of the mean. Okay, and then I'm going to change colors here, and on the same dot plot, mark off 2 standard deviations. So to do that, we got to figure it out. 0.4 plus 0.089 plus another 0.089. That comes out to be, I did this ahead of time to save time, 0.578. So this is 2 standard deviations above the mean. And now we're going to subtract 2.089s. And that gives me 0.222. So this is 2 standard deviations below the mean, and 0.578 is 2 standard deviations above the mean. So we're going to mark that now, 0.22 to 0.578. And I'm going to color that in. Okay. So as you could tell, almost everything is within 2 standard deviations of the mean. There's only a couple. The only ones that didn't fall within that range are right here. These guys right there. These couple right here. Okay. Almost everything fell between 2 standard deviations of the mean. All right. And that is one of the main points of our statistics. Everything we do in statistics is, in general, for a known population proportion, it's always going to be the case that about 95% of the outcomes in a simulated distribution are going to fall within 2 standard deviations of the mean. I know it's a lot of vocabulary, but just focus on, if you could just think, get in your head, if I'm 2 standard deviations, within 2 standard deviations, I can go 2 standard deviations below the mean to 2 standard deviations above the mean, just like I drew right there. That's always going to be 95% of the values are going to fall within that range. If it's a normal distribution, if you do it enough times, it's going to be 95% within 2 standard deviations. All right, so we have a new symbol here named p hat. Okay, and p hat is going to be exactly the same as p. The problem is, and it explains it right here, p is a true proportion. We don't really know that unless we're doing a whole population. When we're doing samples, we have to use p hat. Okay, because it's a sample proportion. So p hat, p with a little hat on it, all right, you can see it right here, is for a sample proportion. All right, so suppose you draw a random sample of 36 chips from a mystery bag and find 20 red chips. Find p hat. Well, since it's a sample, we call it p hat. Okay, and again, we know to find a proportion, how many were there out of how big the sample was. So how many red chips did we get? We got 20. How big was the sample? The sample was 36. So 20 out of 36 would be our p hat. In this case, I got to turn my page. In this case, it's 0.56. 0.56. Our p hat is 0.56. Now that we know p hat, we could find our standard deviation without the calculator. We could just do it. Well, I mean, we're going to put this in the calculator, but we're not going to do L1, L2, and all that, right? Okay, so 0.56 is p hat. 1 minus p hat would be 0.44, right? 0.56 and 0.44 adds up to 1. Divide by n is the sample size, 36. So our standard deviation is 0.083. 0.083. 0.083 would be our standard deviation. So if you went 0.083 on each side of 0.56, 0.56 plus 0.083, 0.56 minus 0.083, that's going to give you within 1 deviation of the mean. If you go another 0.083 and another 0.083, that's going to give you 95%. That's 2 standard deviations. All right, so now what's margin of error? Margin of error is 2 standard deviations from the mean. So here is our margin of error formula that you're going to have to memorize. It's just 2 times the standard deviation. The estimated margin of error is twice the standard error, which is the standard deviation. Okay? So Henry and Terrence drew samples of size 50 from a mystery bag. And this is our last example on video here. We're not going to do 5. We're not going to do 5 on video. Okay, don't cross it off. We're just not going to do it. Henry drew 42 red chips. Terrence drew 40. All right, so sample size 50. Henry, okay, so Henry and Terrence. Okay, Henry, Terrence. Henry's p hat. Henry's p hat is going to be, because he drew 42 out of 50. So 42 out of 50 will give us Henry's p hat, and that's 0.84. So that's his sample proportion. Terry's p hat is 40 out of 50, which is 0.80. So he has a smaller p hat than Henry does. He has a smaller sample proportion. Now let's find the margin of error. The margin of error, we're just using the formula. Just practice using this formula right here, okay? 2 times p hat times 1 minus p hat, that would be 0.16 in this case, divided by the sample size 50, and that's going to be 0.104. So for Henry, his margin of error is 1.04, and Terry's margin of error, 2 times, so it'll be 0.80 times 0.20 divided by 50. So Terry's margin of error is going to come out to be 0.113. Okay, so Terry's margin of error is larger than Henry's margin of error. Okay, he drew less red chips. The more red chips you drew, the smaller the margin of error is going to be. And we'll talk more about that. But basically, all you need to understand is how to calculate margin of error with this formula that you do have to memorize. Okay, this is one of the very few formulas you actually have to memorize in this course. All right, so I'll see you in class for some more practice on the margin of error formula and standard error.